My name is Žigon, and I'm project manager at Process Development Department for Viruses and Vaccines here at BS Operation Sartorius. And today we'll present an overview of downstream process of adeno-associated virus purification using monoliths and rapid evaluation of AAV empty-full ratio with the PATfix HPLC system. And accompanying me today is my colleague.
Hello, my name is Blaž Goričar. I'm a project manager in the Process Analytical Development Department, and I'll be showing you all the chromatography data obtained with our PATfix HPLC system in combination with the CIMmultus analytical columns.
So, briefly about the BS operation. We're the leading developer of monolith technology, and we're the only and exclusive producer of CIM convective interaction media monolithic chromatography columns with experience for more than 20 years now, and also a broad employee base now over 200 persons and still growing. We're located in the center of Europe, in Slovenia, where also it's our state-of-the-art facility, which is in ongoing expansion that will increase its productivity, manufacturing capabilities, and services capabilities up to 5-fold, which also consists of both BSL-1 and biosafety level 2 laboratories who also work with the viruses with such demands. We cover a broad range of products covering from preparative and analytical scale, and we're specialists in purification of large biological molecules, especially the ones which are involved in gene therapy and vaccine markets. Since November 2020, we became acquired by Sartorius, and we're now the Sartorius Center of Excellence in Gene Therapy, offering the solutions in downstream processes and the manufacturing for preparative and analytical scale methods. Our product portfolio consists of 3 categories. The first one is the preparative chromatography, second one is the analytical chromatography, and the third one is the development services. And the preparative products are used in the purification of the target molecules and can be scaled up. And the trade name for this product family is CIMmultus. And they're ranging from the sizes ranging from 1 milliliter up to the 40 liter in size. Also available in different chemistries that fits to the need of the client. The second branch is the analytical devices, which are smaller columns used to analyze samples produced by preparative columns, and they're optimized to achieving the best resolution. And such small precise columns require specialized chromatography system called HPLC, and we also offer one in our product line, which is a PATfix that will also be more focusing later on, and Blaž will go through its presentation. Apart from the chromatography columns, BIA offers also service solutions of downstream process development and for analytical method development, particularly in the area that surrounds the viral vector and vaccines purification, as well as plasmid DNA and mRNA, so whole gene therapy field. Our tech support of the clients is of paramount importance, thus available 24/7. One of many successful stories is the co-development of the AAV downstream process with Avexis, now Novartis Gene Therapy, who use our columns to purify Zolgensma, an AAV gene therapy drug used for the treatment of spinal muscular atrophy. And they especially valued our support and speed, which enabled them to scale up to the manufacturing scale. So this is a great contribution. Now, our unique chromatographic approaches are monolithic columns, which are structured in a way that offers convective mass transport without diffusion. CIMmultus columns have radial geometry that enables higher volumetric throughput by increasing the intake surface area and decreasing the bed height. This means that all functional groups are instantly accessible to a large biomolecules, which then results in benefits which are high capacity and flow independent resolution, as well as laminar flow inside of the column is practically shearless, which also then results in higher yields of stress-related sensitive molecules. The preparative line, so the CIMmultus line, columns are prepacked and they are ready to use. There consists of housing of epoxy composite, which is reinforced with carbon fibers that allow higher pressures, and they're also coated with perilene that prevent non-specific adhesion, leaching, and also allow the cleaning with 1 molar sodium hydroxide, which ensures sanitized conditions. Due to supporting the efficient CIP procedure, monolithic column could be used both as a single or multi-use, so it's down to a client which way he prefers. Our portfolio offers a broad range of monolithic columns, ensuring all scales, ranging from analytics, which are 0.1 milliliter in bed volume, through the preparative scale, which are starting from 1 milliliter, all the way up to the pilot and manufacturing scale, where our largest column is 8-liter column or 40-liter column. It's also can be produced on request. Columns share either finger-tight connection or industry standard sanitary three-clamp connection, which enables effortless connection to any chromatography system. Now let's focus on the downstreaming processing and the characterization by analytics as it is performed in bioseparation Sartorius. Since AAV is one of the most used vectors for gene therapy, its entire production and purification should be closely monitored to ensure a safe product. The key to a good downstream processing is understanding the variety of impurity heterogeneity of the upstream sample. So the impurities that are most common can be divided in 2 groups. Those that are process-related, for example, the host cell DNA, host cell proteins, remaining plasmids, and other transfection reagents that are still present from the upstream. And the other group, which is the product-related impurities, which fall to the category of empty capsids, capsid fragments, and also the complexation of such species. To ensure a safe product, all impurities should be monitored in all of the stages, and also their depletion is critical. Here is where the analytics plays an importance. Since AAV are found in over 12 naturally occurring and more than 100 chimeric variants of adeno-associated viruses, each differing in its amino acid sequence and gene of interest, a single platform process is hard to implement, but minor optimization and tweaks do go a long way. Downstreaming starts with harvesting of the cells, either by collection of supernatant or lysing of the cells in lysing of the cell culture in bioreactor. In both approaches, AAV is found in minority relative to the amount of previously mentioned impurities. Therefore, a pre-capture step might be needed to manage such impurities before proceeding to capture step. And bioseparations here offers multiple options for management of such impurities. And among them, here we see labeled, we have the OH chromatography, which is driven by hydrophobic interaction. Then we have the flocculation, tangent flow filtration, solid phase extraction, and important is also the nuclease treatment and acidic precipitation. In this presentation, we will focus on samples which underwent pre-purification using the tangential flow filtration, coupled with the DNase treatment, which was then followed by the capture step using the SO3 column and full enrichment step performed by polishing on a QA column. The shown process that we will review works for every AAV serotypes, but again, fine-tuning and optimization ensures increases in both recovery as well as the purity. A pre-capture step of TFF and nuclease, salt-tolerant nuclease treatment is performed at high salt environment, which contributes to three benefits. The first one is that the conditions with higher salts are beneficial for serotypes that are more prone to aggregation, for example, AAV2. The second one is that the high salt weakens the overall charge between the DNA and protein complexes, therefore enables decomplexation of DNA and histones, and enables better efficiency of the DNA treatment. And the third one is also the sample is ready to be seamlessly loaded to the SO3 capture step with increased capacity due to the repulsion of small peptides and proteins which are found in the flow-through. TFF can be performed in either flat sheets or using hollow fibers, and it's always good to use the largest cutoff that still retains the virus. Industry standard is 100 kilodalton, but also higher cutoffs are usable. The capture step on SO3 is the heart of every AAV purification, and strong cation exchange properties ensure binding of all AAV species to the column, and negatively charged DNA is found in the flow-through or CIP if it's in a complex form with proteins and histones. Elution is performed using a salt gradient or a step gradient to further concentrate the product to the target levels, which are in the range of the product, so 1e to the power of 13. After capture step, AAV is free of any remaining proteins, as shown on the corresponding SDS page. However, both full and empty capsids are still present in such fraction. Before proceeding to the polishing step, it is required to have sample pure of impurities. Otherwise, the capacities could be compromised due to the AAV sample displacement with the impurities which are in abundance. The AAV column is one of the most described columns for separation of empty and full AAVs, but it's also a subject of several patents. CIMmultus QA column will work for any serotype, but enrichment of fulls is dependent on the serotype, on expression system, probably also on the amount of partially fulls, glycosylations, and phosphorizations of the capsids. Opposed to the SO3 purified sample, the sample is typically diluted to alkaline range of pHs of 9 to 9.5 and very low conductivities ranging from 2 to 5 millisiemens that enhance the binding to the column. In general, we see a 1 log reduction of empty capsids in this step. Continuing from the QA, because at BS Separation we are striving constantly to improve our knowledge of the AAV purification, novel ligand formats were launched which enable and improve the separation of AAV empty and full capsids. And the two novel formats against the QA are presented here, which are the Prima S AAV column and Prima T column that both exploit multimodal properties. In essence, they're both with weak anion exchangers with hydrogen bonding interactions, or also in Prima T, it works in the presence of metal ions, could also have a then metal affinity approach characteristics. And especially Prima T, as seen here, purifying the same sample, it has a big potential in separating not just empty and the full capsids, but also it has the potential to separate the partial capsids from full, or in other words, subpopulation of empty and subpopulation of full particles. Once the preparative runs were performed and once the main eluates are collected from the preparative runs, their assessment by HPLC enables various characterization of such samples, which are following the orthogonal approach. And HPLC analytics are performed using our PATfix system and its advanced software. The one that we will focus on today is the estimation of empty full capsids by CIMmec AAV column. The standard process development method for estimation of empty-full ratio is comparison of genomic titer versus total capsid titer. But this method, however, is not accurate and underestimates the empty-full ratio due to the large deviation and low accuracy of the ELISA assay. The two standards for more accurate ratio is based then on the TEM and the analytical ultracentrifuge, but the limitations of both are both cost and time related. Estimations by HPLC showed superb correlation with the two mentioned methods, and it's surpassing both limitations since assays could be performed under 10 minutes per sample. And at this point, I would like to give a word to Blaž, who will go further in depth of the PATfix HPLC system and the evaluation of individual solutions.
So I will now quickly start with an overview of the PATfix HPLC system. So the main system characteristics of our system are that it is biocompatible. That means all the wetted parts of the system are compatible with strong sodium hydroxide. And we can do cleaning in place at the end of the sequence, at the end of each injection, or even during the method. We prefer to do cleaning in place after the salt gradient. For that, we have a quaternary pump, which provides us to develop complex analytical methods with 4 different buffer types. The HPLC system comes with a autosampler and an optional column thermostat, optional fluorescence and mass detector, and the UV detector is part of the standard configuration. So we have this characteristical triple detector setup, UV-Vis fluorescence detector, which provides us for native protein detection and also nucleic acid detection when the sample is marked with specific markers, such as picogreen, for example. And of course, then we have the mass detector, which provides additional insight on the sample itself. Each detector has its own advantages and disadvantages, and this triple combination provides the most detailed information that we can obtain for each analysis of each sample. Because most of the methods are based either on a salt or a pH gradient, each system comes standard with a conductivity and a pH meter as well. These we consider to be critical parameters or signals and are very useful for method development. Some information about the analytical method. We are using the BS Separations CIMmultus analytical column, the AAV full empty column. The buffers that we are using are buffer A is called the loading buffer. It's a BTP at pH 9, so low salt buffer. Then we have a linear 10-minute or 100 CV gradient from 0 to 400 millimolar sodium chloride. That would be the elution buffer. So it's the same as the loading buffer, but with the added salt, also at pH 9. After the salt gradient, we have the already mentioned cleaning in place. So we're using 1 molar sodium hydroxide in combination with 2 molar sodium chloride. This really ensures that all impurities that bound to the column very strongly get cleaned from the column, so they get eluted. And afterwards, we do a column regeneration step where we drop the pH down back to neutral, and then the system, after a few more minutes, then is ready for the next injection of the next sample. So in this case, we're doing cleaning in place within the method. The data that I'll be showing you today will only focus on the linear gradient part, so only on the salt part, because there is where we find the most information of our target analyte, which is the AAV itself, and not all the other impurities as much. First, a little bit of background and a comparison of this triple detector setup. So what we're doing here is we are comparing fluorescence, MALS, and UV-Vis at 260, 280 signals for different empty and full capsid mixtures. So we mixed these capsids in different ratios from 100% empty to 100% full in different combinations. And what is the key point from here is that only the fluorescence detector shows the actual empty-full ratio from the peak areas of the two peaks that you see on the graph here. Both MALS and UV absorbance will overestimate the amount of fulls due to the nature of their physical detector properties. So the fluorescence detector measures protein, right? So what the fluorescence detector actually measures is the capsid protein and not the DNA insert within the protein. Therefore, we get this realistic response of the actual percentage of empty and full. That is shown here where the dots or the triangles, the green triangles, are perfectly aligned with the theoretical black dotted line. If we look at the MALS data, which is the purple data, the triangles are the raw data, and they are inflated. So the MALS will overestimate the amount of full capsids. This data has to then be adjusted with the correction factor to weigh it down to the actual realistic ratios with the correction factor, which in the case of MALS is defined as the full empty molar mass ratio. That is because the response from the MALS signal is not only a factor of concentration, but a factor of the size of the molecule and the molecular weight itself. Since the size of empty and full capsid is the same, therefore, in our case, that is not a contributing factor. Only the molecular weight then is the factor. And because the full capsid has the DNA insert, which itself has some molecular weight, that then corresponds to this difference that we see on the graph. With the UV absorbance, you can see how much the full capsid is actually overestimated. That is because the DNA insert of the full capsid has a much higher extinction coefficient compared to the empty capsid. And that number then overestimates the amount of full signal, right? Since the absorbance signal is a factor of concentration and extinction coefficient. Therefore, we have to adjust this data once again with a coefficient factor. In this case, that would be the ratio of full divided by empty molar extinction coefficient for 260 and for 280 nanometers separately. And this data has to be known. So we need to know the molar masses of the empties and fulls, or we need to know the extinction coefficients of the empties and fulls to weigh down the data. With the fluorescence detector, we can just use the raw data straight from the detector, no coefficient necessary. The key thing here is that it's much easier to get the correction factor for the mouse than it is for the UV. So measuring or calculating the theoretical molecular weight is not that complicated, and it can be done for complex biological samples as well. I will now transition to the presentation of the chromatograms. First of all, I would like to start by just giving you an overview of the method. So what we're seeing here is this triple detector setup. At the top, we have the baseline response for the absorbance. In the middle, baseline response for the protein fluorescence, and at the bottom, we have the mouse scattering signal at 90 degrees angles. This vertical line is the conductivity trace. So here we see from 3 minutes to 13 minutes is the 10-minute linear gradient from 0 to 400 millimolar sodium chloride, or in our case, from close to 0 to 45 millisiemens per centimeter of conductivity. This is the elution part of the method, where we will see our target analyte to elute during this linear step. So the first sample that we have to show is the harvest sample. So this is straight from the bioreactor. What we can see here is that we have, on the UV fluorescence, we have multiple peaks present. So there are a lot of impurities present in this sample. Mainly what we see is that the 280 line, which is the blue line, is dominant. That means that we have mainly host cell protein dominant impurities. That is then confirmed with the protein fluorescence chromatogram in the middle. And just looking at these two detectors, it would be very hard to pinpoint which of these peaks corresponds to the AAV, since multiple peaks of the impurities are overlapping with the target analyte, the AAV. Looking at the mouse detector, here we can see the first real true benefit of the mouse detector that is used in our PATfix HPLC system. We can see this great selectivity, and the empty and full peaks are clearly visible even in the crude harvest sample. So what we're doing here is we are taking advantage of the nature of the mouse detector, where the response of the mouse is not only a function of the concentration, but a function of molecular weight and size as well. In this case, since the virus, the AAVs, empties, and full capsids have a much larger size and molecular weight than all the other impurities, such as host cell protein, those become the dominant factor that contributes to the response of the signal and not the concentration. Therefore, we are taking advantage of this natural physical property. And what we then see here is we can see and even calculate the empty and full ratio straight from the harvest sample. Of course, as I mentioned on the previous slides, this data has to be corrected with the correction factor. For the mouse, this factor is not very big. It's usually in the range of 1.2 to 1.5, let's say. So the amount of fools here is overestimated by a factor of 1.2 to 1.5, somewhere in that range. It depends on how large the DNA insert is. And of course, that has a fine value because only a certain amount of DNA can fit inside the protein capsid. Just looking at the fluorescence or the UV, it would be almost impossible to tell which peak corresponds to empty and which peak corresponds so to the empty, which is the first one, or to the full, which is the second one here. So if I do like a zoom in of this area where we have the AAV, we can see here on the UV, this peak corresponds based on the mouse to the full capsid, and then the empty capsid with the fluorescence, it's very hard to tell which peak is which. Also with the UV, it's very hard to find out this. So if I then move to the next slide, that would be the intermediate sample. This is the sample that was purified on the CIMmultus column. What we are left here is only with the two virus capsids, so the empty and the full capsids. What we can do here is we can calculate the ratio 260 by 280. For the empty capsids, it's going to be in the range of 0.6. For the full capsids, it's going to be higher than 1.3. So anywhere between 1.3 gives you an indication that these are dominantly full capsids. From the fluorescence, we can then estimate the empty full ratio. So here we have 43% full and 57% empty. And at the bottom, we have the scattering signal as well. So the data from either scattering or from the UV would have to be adjusted to match then the response from the fluorescence. This sample was then further purified on the second CIMmultus chromatography step, and here we are seeing now the discarded sample. Those are the empty capsids. This is the one that we wanted to get rid of in the purification step. Once again, we have here an estimation of empty capsids ratio of more than 95%. So these are, what we see here is just one empty peak with a short tailing, then indicating just a few percentage of fulls left. That means also that we have very good recovery from the second chromatography step. The next sample then is the final product. That would be the full capsids. So this is the product that we would actually then use. What we can see here is very high ratio, 260 to 80 by of 1.33. That indicates mainly full rich dominant sample, which is then further confirmed with the fluorescent signal, since there is only a short fronting visible here, which indicates less than 5% of empties left. Since here the separation between the empties and fulls, it's not perfect. It's not then possible to give a more accurate estimation than more than 95% full capsids. Same on the mouse, we can see this shoulder on the left side here, this very small amount of empty capsid present. If this were really 100% pure sample, we would see a straight vertical line, as we can see then here on the upper part of the chromatogram. That part would just continue straight down. So this smaller triangle here corresponds to the amount of empties, this area of the peak, and once the calculation is done, that then corresponds to less than 5%. So if we now focus on each signal individually, here we have an overlay of absorbance 260, all four samples now. So the black line shows the harvest sample, the purple line shows the intermediate product, and then we have the empty discarded product and the final product, the full. So now we can really see which peak corresponds to the full capsid in the harvest sample. That would be this peak here, and this peak here corresponds to the empty capsids. Because the retention time is the same, so if you then overlay your final product with your starting material, you are then able to identify which peak corresponds to which component. So, and of course, then here we have in the intermediate product, we have the two areas, which of course, just looking at the percentage, 16 and 83%, this area has to be adjusted with the correction factor. So this is just the raw data, which is not applicable to any kind of actual ratio. So the same goes for 218 nanometers. So here the story is very similar, except that with the 280, the proteins have an even bigger influence on this signal. But other than that, a very similar story. So with the black line, we have the harvest. We can see mainly all of the protein dominant impurities. The correction factor for the 280 will be less than it is for 260 because 280 measures mainly proteins. So the DNA insert will contribute less to the error, but still what we have here is an area of 28 and 71%. So a completely overestimated amount of full percentage. This data also then has to be adjusted with the correction factor. The next slide shows then the overlay of the fluorescence signals. Here, the data that we get from the fluorescence is the actual data for the intermediate purified sample. So here we get, let's say, if we look at area, we get close to 50-50 percentage of empties and fulls. Or if we look at only the height ratio, we get 56 and 43%, somewhere in that range. So due to the peaks not being separated 100%, only having partial separation, in this case, the height usually provides more accurate ratio than the area, since the empty capsid will contribute some area to the full area as well, but not the height so much. So therefore, in this kind of partial separation, we always recommend to use the height ratio and not the area ratio, since that provides a smaller error. That can really be seen if we zoom in here. We can see here where the two separate samples are overlaid, how much of this peak area then is contributed to the full capsid, but only a very small amount of height is contributed. So from this tailing of the empty, only a very small amount contributes then to the full peak. Therefore, this height percentage is the most accurate estimation of empty and full ratio. One more thing here to really say is that estimation of empty and full from the harvest sample is not possible due to all the protein impurities interfering with the signal. They are so all the proteins, host cell proteins, are interfering and are overlapping the target analyte, the AAVs, the empties and full capsids, and therefore an accurate estimation is not possible. for that, we really need the mouse detector, which is then shown here. In this case, it's really a clear story. So as already mentioned, we are taking advantage of the mouse properties where the contributing factor for the mouse signal is not only the concentration, but also the molecular weight and the radius. So when looking at the harvest sample, that actually works to our benefit. Basically, all other impurities have a much smaller size and molecular weight, and then the contributing factor for the signal is much smaller. Therefore, we get this very good selectivity between the AAVs and all the other impurities, which enables us to measure the empty-full ratio straight from the harvest sample. And then in case of purified samples, such as the partially purified purple sample, in this case, this data can then be compared with the fluorescence detector, for example. But of course, once again, I would like to say that the data has to be adjusted with the mass correction factor. And also with the mass detector, we get very good resolution between the two peaks, even better than with the fluorescence. So the mistake by the overlapping peaks will be even smaller. If we take a look here, the first peak, so the empty, has almost no contribution in terms of tailing height to the second peak. Therefore, the overlapping issue is not a contributing factor in this case for this detector. Finally, I just want to show once again all 4 slides in the overlay mode. So here we have, once again, starting at the top, we have the starting material, the harvest sample, all signals now combined. Then in the second one from top is the intermediate product, empties and full capsids. And then the third sample are the discarded empties. And the final sample at the bottom is the final product, the full AAV capsids. That would be the bulk product that would then be used as the drug substance. After 2 chromatography steps, we start with this sample with so many impurities, and then we end with a sample which has more than 95% full capsids. That then concludes our presentation. Thank you very much for your attention. If you have any questions, yeah, please go ahead, and hopefully we can answer them. And hopefully you found this presentation to be interesting.
Well, thank you very much, both of you, for such an informative presentation. Before we get started on the question and answer session, I would like to remind our audience how to submit questions. You can submit questions by typing them in the Q&A box, which can be found on the right-hand side of the presentation window. And the first question is, what is lambda X and lambda M for the fluorescence data?
Yeah, so I can answer that. That will be native tryptophan fluorescence. Excitation is 280 nanometers, emission 350 nanometers. So this is native protein fluorescence, excitation and emission.
Okay, thank you very much. And someone wants to know, why can't you separate the full and empty peaks by flattening the gradient?
Yeah, so if you flatten the gradient, you can improve the separation somewhat, but only to a certain degree, and that was already done on these chromatograms. Full and empty AAVs are very similar molecules, therefore they will elute in the gradient under similar conditions, it's very difficult to separate them completely. And increasing the gradient length will only get you so far, you know. Then you have to do other, let's say, improvements to try to separate them on the baseline. Not just with the gradient, but by completely changing the method or optimizing certain conditions of the method, you know. And all of that was already done here. What you see here are the best conditions that we have with this type of column. With other columns, we see an even better separation. So, those are kind of columns that are, some of them are still under development. They can be obtained as a beta product. More information on that is available on the BS Separations website.
Okay, thank you very much. And someone wants to know, would the empty-full ratio be expected to change upon storage? Is it an approach that regulators may look to support shelf life of the AAV in the dosage form? Is this considered a stability indicating approach, or has it been used successfully for this purpose?
Yeah, I can cover that question. So AAV is quite a resilient species. So usually we don't see changes that occur within a week span if it is kept at fridge conditions, so to 8 degrees Celsius. But we prefer that if we're not using the sample for a prolonged time, we're storing it at -80 degrees Celsius. And if there is a repeated freeze-thawing cycles, let's say more than 10, then we might see some changes in profile. But other than that, so regarding the regulators and how do the certificate of analysis are usually then provided, usually there is a potency assays that are looking more into than the potency and the infectivity of AAV rather than just the shape of the empty full separation.
Okay, thank you very much. And someone wants to know, where do the partially full capsids come out?
Yeah, so the partially full capsids would elute as a third peak after the full peak. So the retention time of those would be higher than the full peak. You would see kind of like a shoulder on the last peak, you know, kind of like a right-hand shoulder. Those usually indicate either damaged particles or, you know, like broken capsids and so on.
Thanks. And what serotype was used here, AAV2 or AAV8?
So the serotype that was used and presented here in the study was AAV28, meaning that it has the capsids of AAV8, but the ITR regions of the AAV2.
Thanks. And have you considered aggregates in separation?
So yeah, the aggregates are usually also then we are characterizing them using an additional the detector that is used for that especially is the MULS signal, which doesn't see just the concentration but also the larger species. So then usually we saw those aggregates and complex versions from the MULS detector.
Yeah, so on the chromatogram you would see them at the same time as the partially broken capsids as a third peak after the full peak, and you would then have to do additional analysis with the MULS detector. Let's call this advanced MULS analysis, where you would then calculate the size of the molecule from that third peak, and you would get a bigger radius of gyration compared to the first two peaks, which are just, you know, pure capsids. So the radius would be higher for aggregates, and this can be done, but it requires then, let's say, additional knowledge and skills on how to obtain this data from the MULS detector.
Thank you. And what is the harvest sample and how much of it is used for the PATfix analysis?
So the harvest sample comes after the upstream is finished, is the sample straight from the bioreactor, the crude harvest. The sample was buffer exchanged and filtered to get rid of all of the solid particles and to achieve binding conditions. And then it was a 500 microliter of the sample was injected on the system.
And thank you. And someone wants to know, do you have a washing step between the leading and the elution step to remove impurities?
So as it was presented here on the preparative scale, for the QA, usually for both for the QA polishing and also for the capture step on the SO3, it usually after the loading it follows with the wash step of the buffer A buffer. So basically the loading buffer conditions. Now we might also go in. This is especially true in the capture step. We might increase further the salt percentage to have this contradictory effect on the retention of the capsids. But usually we don't implement such measures if they're not needed. So usually the only step that it's after the loading is the regular buffer A wash.
Okay, thanks. And we have a question, and someone's asked two questions. So the first one is, what are the flow rates for the preparative chromatography, and how long to the purification to capsids, full and empty, take? And the second question is, how long does the polishing of capsids to greater than 95% full capids take, and what is the amount collected?
Okay, yeah, that's a great question. So it was one of the first slides when also I presented so different sizes of the columns. So different sizes have different flow rates which are recommended. Our, let's say, smallest unit, which is 1 ml column for the preparative scale, it goes from 1 column volume up to 16 column volumes per minute. So that would correspond to 1 to 16 mLs per minute. But the largest unit, so let's say 8,000 milliliter or 8 liter column goes up to just 1 CV per minute, so 8 liters per minute. So it's based on that, but usually because the monoliths have a radial geometry and they have flow-independent resolutions and properties, we usually advise that you go with the fastest flow rate that your chromatography system supports. And in the on a manufacturing scale, that usually corresponds to using 2 to 3 CVs across the scaling up. So that then brings down to approximately 20 minutes for the purification run. Now the loading, it depends. So if you went in the dilution or a buffer exchange approach, but in summary it would be 20 minutes for the separation and then also the loading. And the second question, so follow-up question is how it is. In what is the volume that it elutes? Usually we saw once the optimized conditions are met that the main eluate elutes around 4 to 6 CVs from the column. And this is also how we then define the loading capacity, so that we are in the range of titer that is needed for, let's say, for the drug substance.
Oh, thank you. And why is the loading capacity lower on SO3 compared to QA?
This is basically the both columns have the same capacity. So both are in the ranges of high E14 vector genome per milliliter. But we have to understand that on the QA, we're usually loading already purified samples. So we have just the empty and full species. And maybe some partials and maybe some aggregates, but on the capture step, it is the AAV is in minority compared to all the impurities that are present. So this presence of impurities, it's really limiting the capacity on the capture step. So if we would load the pure sample, they would have the same capacity. But due to the impurities and the strong cation exchange properties of the SO3 step, this is the limiting factor.
Okay, thank you. And someone wants to know which pore size was used.
So the pore sizes that were used here were two different ones. So on the preparative scale, we are using 2 micron channels, as we are calling them in monoliths, because we don't really have pores, but there are channels which are interconnected. Whereas for the analytical scale that Blaž was using and presenting, we're having 1.3 microns, meaning a better resolution and also so sharper peaks. Everything is optimized for the resolution-wise.
Okay, thank you. And someone wants to know, is the analytical column compatible with other common HPLC systems?
Yes, of course. So the BPI analytical columns can be used either with the PATfix HPLC system or any kind of other HPLC system. So not an issue there. Also, then you have to adjust the method for your system, of course, in terms of flow rate and so on. We recommend that you use the PATfix HPLC system, but it's not necessary. So the customer can only choose to buy the columns. They can then develop their own methods, or they can purchase the SOP for the methods, the analytical methods from us. Or they can get the whole package if they want, system, methods, columns, everything. So it's up to them. We are flexible on this part.
Okay, thanks. And is there a difference in impurity levels when using a different harvesting approach, such as lysis secreted?
Yeah, of course. So this is the, let's say, we always work in high association with also the upstream. So whatever you produce in the upstream, that will also then result into the downstream. So favorable, of course, would be without the lysis, because with the lysis you introduce a lot of impurities from cleaving all of the cells and all of the membranes. So you have an excess of host cell proteins and also then host cell DNA, which is released and complex. And if possible, we try to not avoid lysis, but we also then have different lysis options from detergent-wise to also osmotic shock, so with salt treatments that are more favorable. But ideally, all AAV, if possible, if they are secreted by themselves from the cells, they are lower in impurities. However, as we've seen in the production, usually the titers where the secreted AAVs with the secretion are lower compared to the lysis, so it's always a balance between the purity and the yield. Yeah.
Yeah, and how does cleaning in place affect analytical method robustness and reliability?
Yeah, so basically certain samples, such as the harvest sample, they include a lot of impurities, which will bind onto the column so strongly that even the salt gradient will not take them off, so they will not be eluted. Therefore, a CIT step after the salt gradient is necessary to remove all the columns and basically reset the column for the next sample. Otherwise, you can have carryover from the previous sample to the next sample, which is not something that you want. So cleaning in place really ensures that you have a clean column after each injection, and you get basically the reliable data that you're looking for, right? So it will improve the reliability of the method, the robustness of the method, and you can be sure that the data you get from this type of analysis is then accurate.
Okay, thank you. And someone wants to know, in FLD, excessive tailing is always observed. Any suggestions to remove that?
That is a very good question, and it has a two-part answer. The first part, all BPI columns, they have a characteristical tailing. So they have a sharp signal increase at the fronting, and then they always have a tailing, which is kind of then extending, kind of like falling exponentially. So that is characteristical for monoliths, very typical. It doesn't matter what the sample is, it can be, any type of injection, you will always get this asymmetrical peak. So a sharp increase on the left side and then kind of like an exponential tail on the right side, so non-symmetrical peak. That's the first part why you see this, and you see this on all detectors. Why the fluorescent has an excessive tailing is because the fluorescent is more sensitive than all the other detectors. So therefore, you are still seeing the tailing from the sample on the fluorescence because you are more sensitive than the other detectors, right? With UV or MAS, you are then with the tail, the concentration is so low, you are already below the detection limit. So you don't see that tailing anymore, right? But with the fluorescence, you are still seeing the tail since you are still above the detection limit. And let's say an additional answer here also could be perhaps the tailing gives you an indication that there are certain protein-rich impurities or particles present in the tailing itself. That could also be another answer, but to confirm that, you would have to be above the detection limit on all detectors and then see if the tailing is present on all three detectors or only on the fluorescence, right? So, but yeah, as I've said, this is not a disadvantage. I would say this is the advantage of the fluorescence detector, is that it is much more sensitive, and therefore you see the tailing, whether with the other detectors you don't see it.
Well, thank you very much. And why does the correction factor for empty-full estimation need to be used for MALS and UV-Vis, but not for fluorescence signal?
So it doesn't have to be used for the fluorescent signal because we are measuring, with the fluorescence detector, we are measuring native protein fluorescence. As I already mentioned, 280, 350 excitation emission. The way to understand it is that the fluorescence detector does not see the DNA insert. It does not distinguish between the empty and full capsid at these excitation emission values. Therefore, the detector doesn't really care, if it's an empty or a full capsid. For the same amount of concentration, you will get the same response. And regardless if it's an empty capsid or a full capsid, a certain concentration of each will give you the same fluorescence response because they both share the same protein capsid. And the DNA insert of the full will not contribute at this fluorescence settings for native protein, right? So, as already mentioned before, the DNA inserts here is a huge factor with the UV detector due to the extinction coefficient, and it is a factor with the MALS detector as well due to the molecular weight difference.
Okay, thank you. And we have time for one final question, and if you could answer this sort of very concisely, what are the advantages and disadvantages of each detector type used in the presented analytics?
Yeah, sure. So let's start with the UV detector. UV detector is mainly used to estimate 260-80 ratio. So from here, if it is, let's say, 0.6, it is mainly empty capsids, since those are that is the ratio for protein. For very pure fractions, it would have to be above 1.3, let's say 1.35 or 1.33. So you can get this kind of data from the UV detector, 260-80 ratio. That is the main advantage. Also, it tells you what part of the chromatogram is protein dominant, where the blue line is above the red line, and what part of chromatogram is nucleic acid dominant, where the red line is above the blue line of the chromatogram. The disadvantage is that you cannot estimate empty-full ratio from the fluorescence, as I already mentioned, due to the extinction coefficient. With the fluorescence detector, the main advantage is that you can get the empty-full ratio directly from the peak height ratio. As I've explained in the previous answer, the disadvantage is that this only works if there are no interfering host cell proteins. So if there are other impurities that will overlap the two peaks, then the ratio will be, you know, it will be warped, it will be false. So the fluorescence only works for at least partially purified samples. You cannot estimate empty-full ratio from the harvest samples, since that one includes a lot of host cell protein. But then, as you saw from the partially purified sample from the SO3 CIMmultus column, from there we removed the majority of the impurities, then we were able to estimate the empty and full ratio from the fluorescent signal. And with the MOS detector, the main advantage is that you can estimate the empty and full ratio also from the harvest starting material due to the nature of the detector as explained in this presentation. And the disadvantage is that you still have to use the correction factor, same as with the UV. So the ratio obtained from the peak areas or peak heights does not directly correspond to the actual capsid ratio. You have to use the molecular weight correction factor. So as you see, not one detector is perfect. Each one has advantages and disadvantages, and that is why we recommend this simultaneous triple detector setup. So with the combination of all three of them at the same time, you really get the whole picture then, right? And then you can get the most reliable data from this type of analytics.
Well, thank you very much for answering those questions and for a fantastic presentation, but unfortunately we're out of time. I want to thank the audience for attending and for participating in today's event. I would also like to thank our sponsor, BIA Separation, for making today's educational webcast possible. We'd like to ask everyone in the audience to participate in a very brief survey. You can see the survey to the right of your screen. You will receive an email from LCGC alerting you when this webcast will be available for replay. We do invite you to send this announcement to any of your colleagues who may have missed today's live event. Thanks very much for attending, and we look forward to seeing you here again. All the best. Bye.
Bye.